Tonight, we're going to explore the quiet spaces that stretch between the stars and the silent, unhurried currents that are carrying the islands of the universe a little farther apart with each passing moment. Picture, for a moment, one of the most famous photographs ever taken. It is a single image of the night sky, and at first glance it looks crowded, almost extravagant. Spirals and ellipses and soft golden smudges of light are scattered across the dark like a handful of jewels spilled onto black velvet. There are thousands of them. They seem to sit close together, neighbors in a glittering city, near enough that you might imagine drifting from one to the next on a calm evening. The picture is completely true, and the feeling it gives you is completely false. That photograph is the Hubble Ultra Deep Field, first assembled by NASA and the European Space Agency in 2004, and later deepened into an even longer exposure called the Extreme Deep Field in 2012. To make it, astronomers pointed the Hubble Space Telescope at a patch of sky that looked utterly empty, a speck so small you could blot it out with a single grain of sand held at arm's length. There were no bright stars there, nothing the eye would ever pause on. They simply let the telescope stare into that tiny dark window, gathering the faintest trickle of ancient light for the better part of 100 hours of accumulated exposure. And out of what looked like nothing, more than 10,000 galaxies slowly emerged, each one a vast wheeling collection of hundreds of billions of stars. So the crowding in that image is real. Those galaxies are truly there. What the photograph quietly hides is the depth. When you look at it, your eye does something very natural and very human. It reads the picture as a flat plane, the way you would read a painting on a wall, with all those galaxies pinned to roughly the same surface, like lights on a single backdrop. But they are not on a single surface at all. Some of them are relatively nearby, in cosmic terms. Others lie billions of light years farther back, their light having traveled across most of the history of the universe to reach that telescope. The image flattens an almost unimaginable depth into a single sheet. It takes a corridor of space billions of light years deep and folds it down onto something the size of a postcard. The galaxies that look like close companions side by side may in truth be separated by gulfs so wide that the light leaving one of them would need billions of years just to arrive at the next. And the depth runs deeper still than mere distance, because out here, distance is also time. The faintest, reddest little smudges in that image are not only the farthest galaxies in the frame, they are also the oldest. The light from some of them set out roughly 13 billion years ago, when the universe itself was still young, not long after the very first galaxies began to take shape. So that single flat photograph is not only folding billions of light years of space down onto one surface, it is folding nearly the entire history of the universe onto it as well, with the nearer, more recent galaxies sharing the same quiet frame as galaxies we are seeing, almost as they were at the beginning of everything. It is, in the plainest sense, the deepest picture of the sky we have ever taken in visible light, and almost all of what it contains is depth we cannot see. This is the gentlest illusion in all of astronomy. Not a trick anyone is playing on us, simply a limit of how our eyes gather a scene. We see a gathering of islands. We do not see the ocean between them. And that ocean, that quiet dark that fills almost the entire frame, is the real subject of the picture. The galaxies are the foam. The emptiness is the sea. Here is the part of the story this whole journey turns on. That emptiness is not holding still. The dark space separating those galaxies is slowly, patiently growing. Not because the galaxies are racing away through some fixed void like sparks thrown from a fire, but because the space itself, the very fabric stretched between them, is gently expanding. With every second that passes, the distant galaxies in that photograph drift a little farther from one another and a little farther from us. The gulfs widen, and under our best current understanding of the cosmos, they will go on widening, not for a while, not until something pulls them back, but without end. The drift, once started, does not stop. There are two quiet truths woven through that idea. The first is that this growing applies only to the galaxies that have come loose from one another, the ones too far apart for gravity to keep hold. The second is that without end is our best reading of the evidence we have today, and even that is something the newest measurements have begun, very gently, to wonder about. These are not loose threads to feel anxious over. They are simply parts of the story still unfolding, the kind that reward patience rather than worry. For now, it is enough to sit with the simple shape of it. The most beautiful photographs of the universe show us a crowded sky, and the real story inside them is the quiet, dark, widening space in between. So let this be the moment you set the day down. There is nothing to solve here tonight, and nowhere we need to be. You can let your shoulders soften, let your jaw unclench, let the weight of the day settle out of your hands. We are going to move through this slowly, the way you might wander through a quiet observatory long after closing, with all the lights turned low. Every idea will be explained as it arrives, gently, with nothing rushed and nothing demanded of you. If your attention drifts, that is perfectly fine. The cosmos has been doing this for nearly 14 billion years. It is in no hurry, and neither are we. Think of it like a handful of glowing embers scattered across the surface of a wide, dark lake at night. Each ember holds its warmth, steady and intact, casting its small reflection on the water, and the lake beneath them is slowly, almost imperceptibly, spreading outward in every direction, carrying the embers gently apart. None of them flares, none of them goes out. They simply drift, each one a little more alone in the dark with every quiet hour, and the spreading water makes no sound at all. That is the universe we are going to explore, a scattering of warm islands of light holding together in their small families, while the dark between them opens slowly and without end. But before we can truly feel how wide those gulfs are, we need something to measure them with. A number like billions of light years washes over us and means very little on its own. So before we set out across the empty spaces, we are going to build ourselves a ruler, starting close to home, with something we can almost hold in our minds, the size of a single one of those islands of light. To measure an ocean, you first need to know the size of a single island. So before we venture out into the gulfs between galaxies, let us build our ruler patiently, one rung at a time, beginning with something close enough to feel almost familiar. We will measure everything tonight not in miles, which become meaningless very quickly out here, but in time, specifically in the time it takes light to travel. Light is the fastest thing there is, moving through empty space at about 186,000 miles every second. Nothing in the universe outruns it. So if we measure distance by how long light needs to cross it, we are using the fastest possible messenger as our yardstick, and the numbers we get are the most generous numbers there can be. If even light takes a long while to make a journey, then that journey is truly, deeply far. Start with the moon, our nearest companion in space. When you look up at the moon on a clear night, the light reaching your eyes left its surface about 1 1/3 seconds earlier. You are seeing the moon not quite as it is, but as it was a moment ago. Reach a little farther, out to the sun, The sunlight warming your face on a summer afternoon left the surface of the sun roughly 8 minutes before it touched your skin. If the sun were somehow to wink out, you would carry on in full daylight for 8 more minutes before the sky knew anything had changed. These are gentle, almost cozy numbers. A second here, a few minutes there. They are the lowest rungs of our ladder, and they feel like home. Now let us climb. Our sun is one star among an enormous gathering of them, all bound together into the great spiral we call the Milky Way galaxy. It is a slowly rotating wheel of somewhere between 200 and 400 billion stars, wrapped in vast lanes of glowing gas and dark drifting dust, all of it turning together through the dark like a single immense pinwheel seen from very far away. Our sun, with all its planets, sits out in one of the quieter spiral arms, somewhat less than 30,000 light-years from the crowded galactic center, riding along on that slow galactic turn. Even that distance, the span from us to the heart of our own galaxy alone, is so vast that the light leaving the galactic center tonight will not arrive in our sky for tens of thousands of years. It is a beautiful place to live, and it is far larger than the gentle numbers we just used can prepare you for. Here is where the ruler stretches in a way that is hard to hold in the mind. To cross from one side of the Milky Way to the other, light, that same messenger that crossed to the moon in a single breath, would need somewhere between 100,000 and 200,000 years, not seconds, not minutes, 100,000 years and more, moving every single second of that time at 186,000 miles per second, never once slowing down. Let that number rest for a moment, without straining to hold all of it at once. The light that is only now arriving at the far edge of our galaxy set out when our distant ancestors were still learning to shape stone tools, long before the first cities, long before writing, long before recorded history of any kind. An entire span of human becoming has passed in the time it takes a beam of light simply to travel across the place we call home. And the Milky Way is only one island, one, out of an estimated 2 trillion scattered across the visible universe. That is the whole point of building this ruler. From here on, every distance we meet, every gulf between galaxies, every empty stretch of the cosmic dark, we will measure against the width of our own galaxy. When we say that the nearest large galaxy lies more than 2 million light-years away, you will be able to feel it, because you will know that crossing our own galaxy alone already takes 100,000 years of light. The gaps between galaxies are not a little larger than a galaxy. They are many times larger. The islands are vast beyond comprehension, and the water between them is vaster still. Professional astronomers, who chart these spaces for a living, eventually grow tired of writing such enormous numbers of light-years, so they fold them into tidier units. The first is the parsec, which is about 3¼ light-years. That is a little more than the distance to even our nearest stellar neighbor, a small red star called Proxima Centauri, which lies about 4¼ light-years from us, across more than 40 trillion kilometers of empty space, and which is the closest star to us anywhere in the sky other than our own sun. For the truly grand scales, the spaces between whole galaxies, astronomers use the megaparsec, which is a parsec multiplied by 1,000,000. 1 megaparsec is about 3¼ million light-years. You do not need to memorize these. They are simply the surveyor's tools, the way a mapmaker might switch from inches to miles when the territory grows too large for the smaller marking. When these words drift past later tonight, you can let them settle softly, knowing only that a megaparsec is a unit built for measuring the gaps between islands of stars. It helps, sometimes, to shrink all of this down to something you can almost hold in your hands. Imagine a single maple leaf, beautifully detailed, every vein and edge intact, floating quietly on the surface of a wide, dark, still pool of water at night. That leaf is our entire Milky Way galaxy. Every star you have ever seen with your naked eye. Every star in every constellation you could ever name. The sun and all its planets. This whole world and everyone who has ever lived on it. All of it sits within that one drifting leaf. And the pool it floats upon, dark and silent and stretching away in every direction past the reach of any light, is the space between the galaxies. Somewhere far across that dark water, too far to make out tonight, other leaves are floating. We will go looking for the nearest of them soon. For now, simply rest with the leaf. One quiet raft of stars on an enormous dark surface, turning slowly, holding everything you have ever known. We have our ruler now. We know the size of a single island, measured in the patient travel of light, and we know that even the fastest thing in existence needs a span longer than human history just to cross it. That is the unit we will carry with us from here. So the natural question, the one that pulls us gently onward, is the one any traveler asks when they realize how alone their island is. How far away is the next one? Where is the nearest shore across all that dark water? And what would we find if we ever managed to reach it? So we go looking for the next island. And the remarkable thing is that you do not need a telescope to find it. On a clear, dark night in autumn, away from the glow of city lights, you can find the nearest large galaxy with your own eyes. Look toward the constellation Andromeda, and you will see, if your sky is dark enough, a faint and slightly elongated smudge of light. It is dim, easy to overlook, the kind of thing you might mistake for a distant cloud or a smear on a lens. Most people have walked beneath it their whole lives without ever noticing it. But that pale little smudge is not a cloud, and it is not inside our galaxy at all. It is the Andromeda Galaxy, known to astronomers as M31, and it is an entire empire of stars, where our own Milky Way holds a few 100 billion suns. Andromeda holds something on the order of 1 trillion. It is the largest galaxy in our immediate neighborhood, larger than our own, and it is the most distant object that the unaided human eye can see. When the Hubble Space Telescope turned its full attention to Andromeda, the result was one of the largest images the observatory has ever made. As part of a survey called the Panchromatic Hubble Andromeda Treasury, astronomers combined more than 7,000 separate Hubble exposures into a single sweeping mosaic, released in January of 2015. Even across a gulf of 2.5 million light-years, Hubble's vision was sharp enough to pick out individual stars in the galaxy's disk, more than 100 million of them, resolved one by one across a span of more than 60,000 light-years. It is a strange and humbling thing to look at a portrait so detailed that you can pick out single suns, and to remember that every one of those points of light is a star much like our own, with its own quiet history, impossibly far away. That distance, 2.5 million light-years, is where our ruler from a moment ago begins to do its quiet work. Remember that crossing our own Milky Way takes light somewhere over 100,000 years. The gap to Andromeda is more than 20 times that, a stretch of mostly empty space 20-some galaxy widths across. And remember too, that this is the nearest large galaxy, the closest shore. Everything beyond it is farther still. It helps to try to cross that gap with something real, something human hands have actually built. The fastest object our species has ever made is the Parker Solar Probe, a NASA spacecraft designed to skim close to the Sun. In December of 2024, as it swung through its closest approach, it reached a speed of roughly 430,000 miles per hour, faster than anything humanity has ever flung into space. At that breathtaking pace, a speed that would carry you from the Earth to the Moon in well under an hour, how long would the Parker Solar Probe need to reach Andromeda? Around 4 billion years, not 4,000, not 4 million. 4 billion years of travel at the fastest speed we have ever achieved, just to cross to the nearest large island of stars. By the time it arrived, our Sun itself would be nearing the end of its life. And here is the gentlest thought of all, the one worth resting on for a while. The faint smudge of light you can see on an autumn night did not leave Andromeda recently. Those photons, the actual particles of light entering your eye, began their journey across the dark roughly 2.5 million years ago. They set out long before there were any humans to receive them. 2.5 million years ago, our ancestors were early, upright walkers on the African plains, before our own species had emerged, before the genus Homo had fully taken shape. The entire arc of human becoming, every tool and fire and word and city, all of it fits comfortably inside the time it took that light to reach you. When you find Andromeda in the sky, you are not seeing it as it is tonight. You are seeing a ghost, a portrait of how it looked before we were us, delivered to your eyes across an unimaginable stretch of patient time. There is something tender in that, rather than something lonely. The light kept its appointment. It travelled all that way, across all that dark, and arrived exactly on the night you happened to look up. There is also far more to Andromeda than the bright disk of stars we can photograph. By analysing 5 years of archived Hubble observations, astronomers found that the galaxy is wrapped in an enormous, nearly invisible halo of hot gas, far larger and far more massive than anyone had realized. This dark halo reaches out roughly 1 million light-years from the galaxy, which is something like halfway across the gulf toward our own Milky Way. They could not see it directly, because the gas is dark and gives off almost no light of its own. So they did something patient and clever. They used the light of distant quasars, the brilliant cores of far-off galaxies, shining from behind Andromeda, and watched how that light dimmed at particular wavelengths as it passed through the unseen gas. From that faint dimming, they measured the halo's vast reach. If we could somehow see that halo with our eyes, it would stretch across our sky 100 times wider than the full moon. Our nearest neighbour, in other words, reaches toward us through the dark far more than its visible edge would ever suggest. And now, the first quiet turn in our story, the first thread of the larger picture we promised at the very beginning. You might expect that this distant island, like the galaxies in that deep field photograph, is drifting away from us, carried off by the expanding space between us. But Andromeda is not receding. It is one of the rare large galaxies in all the sky that is actually moving toward us, drawing slowly closer with each passing year. Out among the truly distant galaxies, the dark gulfs are widening without end. Here, close to home, something different is happening. Something is holding Andromeda and the Milky Way together, refusing to let the cosmic tide pull them apart, and gently reeling them toward one another instead. For now, simply hold the strangeness of it lightly. The universe, as a whole, is letting its islands drift apart, and yet our nearest neighbour is coming home to us. Both of these things are true at once, and the reason they can both be true is one of the loveliest ideas in this entire story. Picture, then, a distant lighthouse standing on a dark and quiet coastline, far across a wide expanse of still black water. Its beam reaches out across the emptiness, traveling for a very long time before it ever finds your eyes on the opposite shore. By the time the light arrives, the keeper who lit it may be long gone, the night it was kindled long past, and yet there it is, faithful and warm, a small steady glow carried to you across all that dark. That is Andromeda on an autumn night, ancient light still arriving from a shore we could never hope to reach, drawing quietly nearer all the while. We have found the nearest island now, and learned that it is both unimaginably far and, against all expectation, a member of our own small family. So the question turns naturally inward. If Andromeda is bound to us, held close while the wider cosmos drifts apart, then what exactly is this family we belong to? Who else lives on our side of the great dark water? And what is it that keeps us all together while everything beyond goes its separate way? The answer is that we are not alone out here, drifting as a single leaf on the dark water. We belong to a family. Astronomers call it the local group, which is a plain and almost cozy name for what it actually is, the small gathering of galaxies that we are gravitationally bound to, the ones traveling through the cosmos alongside us, held close by their mutual pull. It is our neighborhood, our archipelago, the cluster of islands on our side of the great dark sea. And like any neighborhood, it has its prominent residents, its quiet ones, and its many small homes you might never notice unless you went looking. The local group spans roughly 10 million light-years from end to end. That is already a hard number to picture, since crossing our own galaxy takes light 100,000 years, and this neighborhood is about 100 galaxy widths across. Within that span live somewhere between 50 and 80 major galaxies, and when you count the faintest members, the dim little dwarf galaxies that hold only a handful of stars compared to their giant neighbors, the tally climbs to well over 100. Most of these are small and shy, easy to miss, orbiting quietly around the larger members like moons around planets. But the structure of the whole family is shaped by just two great anchors. Those two anchors are the Milky Way, our own home, and Andromeda, the nearest shore we visited a moment ago. Together, they hold most of the family's weight, sitting at opposite ends of the neighborhood like two heavy stones, with the smaller galaxies scattered around and between them. If you could somehow step far enough back to see the entire local group at once, you would notice that it is shaped a little like a dumbbell, with our Milky Way clustered with its companions at one end, Andromeda clustered with its own companions at the other, and the long span of space between them holding the two groupings in a slow gravitational embrace. There is a third member worth naming, the next largest after the two giants. It is the triangulum galaxy, known as M33, a graceful spiral holding perhaps 40 billion stars, lying around 2.5 to 3 million light-years away. It is smaller than either the Milky Way or Andromeda, a junior member of the family, but it is a true spiral galaxy in its own right, and it rounds out the trio of the neighborhood's largest residents. Below these three, everything else is dwarfs and stragglers, the small quiet homes of the archipelago. Our own Milky Way, like Andromeda, travels with a retinue of these smaller companions. The two most prominent are the large and small Magellanic Clouds, a pair of irregular dwarf galaxies that can be seen with the naked eye from the southern hemisphere, glowing softly like detached pieces of the Milky Way itself. The larger of the two, the large Magellanic Cloud, lies about 160,000 light-years away and holds something like 1/10 as many stars as our own galaxy. Closer in, and only recognized in more recent decades, is the Sagittarius dwarf galaxy, a small companion that the Milky Way's gravity is slowly drawing in and stretching apart. And astronomers keep finding more of these faint little satellites, galaxies so dim and so sparse that they escape notice for a very long time. The family, it turns out, has many more quiet members than we once believed, and we are still taking the full census of everyone who belongs to it. Now we come to the part that matters most tonight, the part that turns this from a simple list of neighbors into something genuinely comforting. This whole family has come loose from the expansion of the universe. Remember the central idea of our story, the one we planted at the very beginning. The space between distant galaxies is stretching, carrying them apart, and under our best understanding it will not stop. But the stretching only wins out across the truly vast, empty gulfs, where there is nothing strong enough to resist it. Here, inside the local group, the mutual gravity of all these galaxies pulling on one another is stronger than the gentle, outward stretch of space. And because gravity wins here, our neighborhood has done something remarkable. It has decoupled from what astronomers call the Hubble flow, the great outward drift of the expanding cosmos. The space inside our family is not stretching. Our galaxies are not being carried apart. The local group long ago settled into its own balance, bound together, holding its shape, riding through the wider universe as a single connected whole. This is why Andromeda, which we found drifting toward us rather than away, can be moving closer at all. It is not fighting the expansion. The expansion simply does not reach inside our family to begin with. Within these 10 million light years, gravity has the final word, and gravity is keeping us together. It is worth letting that settle, because it gently reshapes the whole picture. The universe is not pulling everything apart. It is pulling apart the distant, the unbound, the islands too far from one another to hold on. But the small family each galaxy belongs to, the cluster it is gravitationally tied to, stays. We are not adrift and alone, watching our neighbors recede into the dark one by one. We are moored. The wider sea may be widening without end, but our little harbor holds, and it will go on holding long into the future. Picture a small cluster of boats moored together in a quiet, sheltered harbor at night. They sit side by side, gently rocking, their lines tied to the same set of posts, rising and falling together with the soft motion of the water beneath them. Outside the breakwater, the open ocean swells and stretches away to the dark horizon, vast and restless and endless. But inside the harbor, the boats stay close. The tide that pulls at the wider sea does not scatter them. They were tied together long ago, and they remain together, a small, steady gathering of lights on the water, while the great dark ocean opens out beyond the walls. That is our local group, a handful of galaxies moored in the same harbor, held by the patient grip of gravity, staying close while the rest of the cosmos drifts gently apart. Whatever happens out in the wide, expanding dark, this much is steady, this much holds, so we can rest a little easier knowing the family stays together. But that raises a natural curiosity about the other side of the harbor wall, the open sea itself. We have spoken of the gulfs between galaxies as empty, as dark water, as the real subject hiding inside every deep-field photograph. But what is actually out there, in those vast spaces between the islands? Is it truly nothing at all, a perfect and total void? Or does even the emptiest dark hold something, thin and quiet, waiting to be found? The honest answer is that the space between galaxies is not perfectly empty, but it comes astonishingly close, closer to true nothingness than anything we could ever build here on Earth. Let us start with how thin it really is, because the comparison is hard to believe until you sit with it. The air around you right now, the ordinary air filling your room, is dense with molecules. In a single cubic centimeter of it, a space about the size of a sugar cube, there are roughly 10 billion atoms, all jostling and colliding millions of times a second. That is the air we move through so easily that we forget it is even there. Now travel out into the deep space between galaxies, far from any star, into the great dark gulfs we have been measuring. Out there, the average density drops to something on the order of a single atom in an entire cubic meter of space. One atom, drifting alone, in a volume large enough to hold a person. The emptiness is so complete that the finest vacuum chambers ever built in our laboratories are crowded, bustling cities by comparison. It is worth pausing on just how empty that is, because even the space inside our own galaxy is far from full. The space between the stars, what astronomers call the interstellar medium, is itself thin almost beyond imagining, holding on average only about one atom in every cubic centimeter in that same sugar cube of space. That alone is already millions upon millions of times emptier than the air in your room. And yet, the space between the galaxies is emptier still, thinner by roughly another factor of 1,000,000. To find a single atom in the deep intergalactic dark, you would have to search on average through a full cubic meter of space. As one astronomy text puts the matter plainly, most of the universe is fantastically empty, and the dense places, the stars and the planets and the people, are the rare and precious exceptions. And yet, for a long time, that near-perfect emptiness held a genuine mystery, one that troubled astronomers for decades. When they added up all the ordinary matter in the universe, the familiar kind made of atoms, the kind that forms stars and planets and people, the kind astronomers call baryonic matter, the numbers did not balance. Our best models of the early universe predicted a certain total amount of this ordinary matter, and the prediction is quite precise. But when astronomers went looking for it all, counting up the matter locked into stars and galaxies and glowing clouds of gas, they could only find about half of it. Roughly 40 to 50% of the normal matter that should exist seemed to be missing. Not exotic dark matter, which is a separate puzzle entirely, but ordinary atoms simply unaccounted for. It became known as the problem of the missing baryons, and for years no one could say where they had gone. The answer, it turned out, was hiding in the very emptiness we have been describing. The missing matter was spread out across the vast intergalactic gulfs in a form so thin and so faint that it had escaped detection. Astronomers gave it a name, the warm-hot intergalactic medium. It is a wispy, electrically charged gas, threaded invisibly through the spaces between galaxies, holding a large share of all the ordinary matter in the cosmos in a veil too diffuse to see directly. Finding it required real ingenuity, and the story of how it was confirmed is a quietly beautiful piece of modern astronomy. In 2018, a team of astronomers led by Fabrizio Nicastro published their results in the journal Nature. They did not photograph the gas because it is far too faint to photograph. Instead, they used distant quasars, the blazingly bright cores of remote galaxies, as backlights. When the light from a quasar passes through the thin intergalactic gas on its long journey to Earth, certain atoms in that gas absorb very specific colors from the beam, stamping faint dark lines into the light spectrum like a fingerprint. It was the same patient idea that had revealed Andromeda's invisible halo, the watching of distant quasar light for the marks left by unseen gas, now turned outward onto the open gulfs between the galaxies. Nicastro's team found the signature of highly ionized oxygen, oxygen stripped of most of its electrons, written into quasar light, and that fingerprint revealed the hidden gas at last. Then, in 2020, a second team, led by Jean-Pierre Macquart, also publishing in Nature, confirmed the picture from an entirely different direction. They used mysterious flashes called fast radio bursts, intense pulses of radio energy arriving from far across the universe. As one of these bursts travels toward us, the thin scattering of charged particles in the intergalactic medium slows its different frequencies by different amounts, smearing the pulse out in a way that depends on exactly how much matter it passed through along the way. By measuring that smearing, Macquart and his colleagues could weigh the intervening gas, and their measurement matched what was expected. Between the two methods, the missing baryons were found. They had been resting all along in the emptiest places in the universe. There is one more thing about this intergalactic gas that is worth dwelling on, because it sounds like a contradiction and turns out to be perfectly true. The warm-hot medium is, by one measure, scorchingly hot. Its individual particles can carry temperatures of hundreds of thousands, even millions of degrees, and yet, if you could somehow pass through it, you would feel nothing at all. You would feel cold. You would feel, in fact, like you were moving through perfect empty nothing. How can something be millions of degrees and still feel freezing? The resolution lies in what temperature actually means. Temperature is a measure of how fast individual particles are moving, how much energy each one carries. The few atoms drifting through intergalactic space are indeed moving extraordinarily fast, so by that measure the gas is genuinely hot. But warmth, the kind you can feel, depends on those particles actually striking you again and again, transferring their energy into your body. And out there, the particles are so unimaginably sparse, so far apart, that almost none of them would ever reach you. There is plenty of energy in each one, and almost no one to deliver it to. The gas is technically scorching and effectively freezing, both at once, simply because there is so very little of it. It is a gentle reminder that the universe does not always behave the way our everyday intuitions expect, and that the strangeness is not something to fear, only something to notice with a little wonder. Picture, then, an ultra-faint warm mist, so impossibly thin that it is invisible, hanging across an enormous dark valley at night. Each tiny droplet within it glows with its own fierce inner heat, but the droplets are spread so far apart that a traveler walking through the valley would pass between them for miles and miles, never touching more than a handful, feeling only the cool, silent, empty air of the open dark. The mist is there, the heat is real, and the path through it is quiet and cold and seemingly empty all the same. That is the ocean between the galaxies, an ocean with almost no water at all, holding half the ordinary matter of the cosmos in a veil too thin to feel. So the great gulfs are not truly empty, only nearly so, and even their faint contents have now been found and weighed. But we have been picturing these spaces one gap at a time, the distance to a single neighbor, the span of a single family. If we pull back much farther, far enough to see how the galaxies are arranged across the whole sky, a larger pattern begins to emerge. The galaxies are not scattered at random through the dark. They are arranged, it turns out, into a vast and delicate structure, and the shape of that structure reveals something surprising about where all this emptiness truly lives. When astronomers first began mapping where the galaxies actually sit, plotting them out in 3 dimensions across great swaths of sky, they expected something fairly even. a scattering of galaxies sprinkled more or less uniformly through space, the way grains of sand might settle across a beach. That is not at all what they found. Instead, the galaxies trace out one of the largest and most delicate structures in all of nature, a pattern astronomers call the cosmic web. Across hundreds of millions of light years, matter gathers itself into long glowing filaments, slender bridges of galaxies strung together like beads on threads. Where several filaments meet, they swell into dense, brilliant nodes, the great clusters where galaxies crowd most thickly. Between the filaments, matter spreads into broad, thin sheets, like walls of light, and the whole intricate scaffolding, the filaments and the nodes and the sheets, wraps itself around something far larger and far emptier. It wraps around vast, round, almost perfectly empty bubbles, enormous spherical regions where there is very little of anything at all. Astronomers call these bubbles voids. This is where the picture turns gently on its head, in a way worth pausing over. We naturally think of the universe as a collection of galaxies with some empty space in between. But when you map the cosmic web honestly, you find the opposite is closer to the truth. The voids, those great empty bubbles, take up around 80% of the entire volume of the universe. The bright structure we see, all the filaments and clusters and shining galaxies, is the thin exception. The delicate film stretched across the surfaces of the bubbles. The emptiness is not the gap in the design. The emptiness is the design. The galaxies are simply the foam clinging to the edges of an ocean made almost entirely of empty space. Astronomers who map this structure often reach for homely comparisons to describe it, likening the whole arrangement of filaments and voids to a kitchen sponge, or the inside of a honeycomb, or a hunk of Swiss cheese riddled with very large holes. The galaxies cling to the thin walls and arcs that surround the holes, and the holes themselves, the voids, are typically something like 150 million light-years across. When you tally it all up, the picture is stark and rather beautiful. Roughly 90% of all the galaxies are crowded into less than 10% of the volume of space, and all the rest of space is the quiet emptiness of the voids, holding almost nothing at all. Before these great holes were discovered, most astronomers had simply assumed that the regions between the giant clusters would be filled with small groups of galaxies, or at least with scattered single ones. But careful searches inside the voids turned up very few galaxies of any kind. The emptiness was real, and it was enormous. To make this real rather than abstract, it helps to visit two of these voids by name, because astronomers have found and measured them, and their scale is genuinely difficult to hold in the mind. The first is the Boötes void, named for the constellation in whose direction it lies. It was discovered in 1981 by a team led by the astronomer Robert Kirshner, working with his colleagues Augustus Oehmler, Paul Schechter, and Stephen Schechtman. They were surveying galaxies in that region of sky and found, to their surprise, a tremendous hole. The Boötes void stretches roughly 330 million light-years across, and it sits some 700 million light-years away from us. To grasp how empty it is, consider that across a region that size, the normal density of the universe would predict perhaps 2,000 galaxies. Inside the Boötes void, astronomers have found only about 60. It is so vast and so empty that one astronomer later remarked that if the Milky Way had been born at its center, we would not have known other galaxies existed until well into the 20th century. There would have been almost nothing close enough to see. The second void is even larger, and it is closer to home in a way that may surprise you. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, published evidence for an enormous underdense region surrounding our own corner of the universe. It is now known as the KBC void, after their initials. It spans something on the order of 2 billion light-years across, and within it, the density of galaxies runs roughly 20% below the cosmic average. What makes it remarkable is its location. Our own Milky Way, our local group, our whole familiar neighborhood, appears to sit inside this great quiet bubble, well within one of the largest underdense regions yet charted. We do not live in a typical average patch of the cosmos. We live, it seems, in a particularly empty one, a wide hollow in the cosmic foam. So the deep field photograph we began with, the one that looked so crowded with light, was telling us the truth in a way we did not expect. The galaxies really are scattered like islands, but the dark around them is not merely the gap between the islands. The dark is the sea those islands float upon, and the sea is most of everything there is. Picture a cluster of soap bubbles gathered in a dark and quiet room, the kind a child might blow and watch drift through a shaft of light. Look closely at where the water actually is. It is not filling the bubbles. It clings to the thin, glistening curved walls, the shimmering surfaces where one bubble presses against the next. All the substance, all the shine, all the structure rides on those delicate films. And the great rounded interiors, the vast majority of the space the bubbles enclose, hold nothing but still, quiet air. That is the cosmic web. The galaxies are the shimmer on the walls. The voids are the quiet air within, and almost all of the room is air. There is one last thing to notice before we move on, and it is the thread that carries us into the heart of our whole story. These bubbles are not fixed in place. They are not a finished, settled structure that the universe arranged once and left alone. The galaxies and clusters themselves, held firmly by their own gravity, do not expand, but the voids between them do grow larger, and the filaments are eased steadily farther apart as the space itself stretches. Slowly, patiently, the great empty bubbles are swelling outward, pressing gently against the bright threads of galaxies that wall them in, easing those threads farther and farther apart. The foam is being stretched. The architecture of the cosmos is in slow, quiet motion, and the spaces are opening wider with every passing age. That brings us to the deepest question of the entire night. Why should the space between galaxies grow at all? What is it that sets the islands adrift in the first place? To answer that, we travel back almost exactly 100 years to a quiet observatory on a mountainside in California, and to the patient, careful man who first noticed that the whole universe was on the move. The mountain is called Mount Wilson, rising above the city of Los Angeles, and in the 1920s it held the most powerful telescope in the world. The man who used it was Edwin Hubble, a careful and methodical observer who would spend long cold nights at the eyepiece, photographing faint smudges of light that no one yet fully understood. At the time, it was not even settled whether those smudges were small clouds within our own Milky Way, or vast separate galaxies far beyond it. Hubble's patient work would help prove they were galaxies, islands of stars in their own right. But his greatest discovery was still to come, and it would quietly rearrange humanity's whole picture of the cosmos. He was building on the work of others, as careful scientists always are. More than a decade earlier, around 1912, an astronomer named Vesto Slipher had been studying the light from distant spiral nebulae, the objects we now know as galaxies. When Slipher spread their light out into a spectrum, the way a prism spreads sunlight into a rainbow, he noticed something curious. The dark lines in those spectra the fingerprints left by particular atoms, were shifted from where they ought to sit. In most of the galaxies he studied, the lines were nudged toward the red end of the spectrum. This shifting toward red is called redshift, and it happens when the light waves arriving from an object are stretched longer than the waves it sent out. Slipher had found that the distant galaxies were almost all redshifted, but he could not yet say what the pattern meant. Hubble took the next step. Using the Great Hooker telescope at Mount Wilson, then the largest in the world, he measured not only the redshifts of galaxies, but also their distances. To measure those distances, he relied on a discovery made years earlier by Henrietta Swan Leavitt, an astronomer at the Harvard College Observatory. Studying a kind of pulsing star called a Cepheid variable, a star that brightens and dims in a steady, reliable rhythm, Leavitt found in 1908 that the slower a Cepheid pulsed, the brighter it truly was. This period luminosity relation was a quiet revolution, because it meant that by simply timing a star's heartbeat, an astronomer could work out its true brightness, and from its true brightness, its distance, no matter how far away it lay. Hubble found Cepheids in distant galaxies, used Leavitt's relation to gauge how far those galaxies were, and set their distances against their redshifts. And in 1929, he published a relationship so simple it could be written in a single line, yet so profound it reshaped cosmology. The farther away a galaxy was, Hubble found, the faster it appeared to be receding, and the relationship was beautifully proportional. A galaxy twice as far away receded twice as fast. A galaxy 10 times as far receded 10 times as fast. We now write this as a clean little equation, the recession velocity equal to a constant multiplied by the distance, and we call that constant the Hubble constant. There is a quiet matter of fairness worth mentioning here, because science is a human endeavor, and credit can take time to settle. 2 years before Hubble's paper, in 1927, a Belgian priest and physicist named Georges Lemaitre had already worked out, on purely theoretical grounds, that the universe should be expanding. He derived it from Einstein's equations of general relativity and even estimated a rate, but his paper was published in a small journal in French and went largely unnoticed. For decades, the discovery carried Hubble's name alone. In 2020, the International Astronomical Union formally recommended that we call it the Hubble-Lemaitre law, restoring the quiet priest to the story he helped begin. Now we arrive at the detail almost everyone gets wrong at first, so let us take it slowly and gently. When we say the galaxies are receding, it is natural to imagine them as objects flying outward through space, like fragments hurled from some great central explosion, racing away from a fixed point with us somewhere near the middle. That picture is wrong, and the truth is stranger and far more elegant. The galaxies are not flying through space. They are, for the most part, sitting quietly more or less where they are, each one resting in its own local patch of the cosmos. What is changing is the space itself. The fabric of space between the galaxies is stretching, expanding in every direction at once, and as it stretches, it carries the galaxies along with it, easing them apart the way two marks on a balloon ease apart as you blow it up. That balloon is one of the two images astronomers reach for to make this clear, and it is worth holding in your mind. Imagine dotting the surface of a balloon with small marks, then slowly inflating it. Every mark moves away from every other mark. From the point of view of any one dot, all the others appear to recede, and the farther away a dot is, the faster it seems to pull away. Yet no dot is moving across the surface of the balloon. They are all staying put. It is the rubber between them that is growing. And notice that there is no special center on the surface, no dot that everything else is fleeing from. Every dot sees the same thing. Every dot could believe itself to be the center, and every dot would be equally right, which is to say, not the center at all. The other image is a loaf of raisin bread rising slowly in a warm oven. As the dough expands, every raisin drifts away from every other raisin. A raisin on the far side of the loaf recedes quickly, because there is so much expanding dough between it and you. A nearby raisin drifts off gently, because there is less dough in between to grow. No raisin is moving through the dough under its own power. They are all simply being carried apart as the space between them swells. That is our universe. We are one raisin among trillions, watching the others recede, not because anyone is fleeing, but because the dough of space itself is quietly rising. This is what the title of our journey means when it speaks of the distance between galaxies growing. It is not motion through space. It is the patient swelling of space itself. There is one more thread to lay down here, and it is a live and genuine puzzle in astronomy today, the kind of honest, open question that makes the science feel alive rather than finished. To use the Hubble-Lemaitre law, you need to know the value of that constant, the rate at which space is expanding. And here, a curious disagreement has emerged. When astronomers measure the expansion rate using the light of the early universe, the faint afterglow of the Big Bang, mapped in exquisite detail by the European Space Agency's Planck satellite, they arrive at a value of about 67 kilometers per second for every megaparsec of distance. But when other astronomers measure it a different way, by carefully building a ladder of distances out to relatively nearby galaxies using bright stars like the very Cephids that Leavitt first understood, and the work of teams led by the astronomer Adam Rees, they consistently get a higher number, closer to 73. Those two numbers should agree. They are measurements of the same universe, the same expansion, and yet they stubbornly do not, and the gap between them has not closed as the measurements have grown more precise. If anything, it has sharpened. Astronomers call this the Hubble tension, and it is one of the most interesting unsolved problems in cosmology right now. It may mean there is some subtle flaw in how we are measuring, or it may be a hint, a small crack in our understanding, pointing towards some new physics we have not yet grasped. No one knows yet, and that not knowing is not a worry. It is one of the open doors that makes this field so quietly thrilling. Picture, finally, a soft dark ribbon of rubber lying flat in the dark, with two small ladybugs resting upon it, a little apart from one another. Now imagine a gentle hand slowly, evenly stretching that ribbon from both ends. The two ladybugs drift apart. The distance between them grows steadily, and yet neither ladybug takes a single step. They sit perfectly still, resting where they always were, carried apart by nothing but the quiet stretching of the surface beneath them. That is every galaxy in the expanding universe, our own included, resting in place, drifting apart, carried by the patient growth of space itself. We understand now that space is stretching, and that this is why the distances grow, but that only deepens the central promise of our title. For the expansion is not merely continuing at a steady pace, it is speeding up. And the reason it speeds up is one of the deepest mysteries in all of science. Picture a tide going out on a wide, flat shore at dusk. The water draws back slowly, patiently, and you might expect it eventually to pause, to gather itself, and to turn and come flowing back the way it always has. But this tide does not turn. It keeps drawing back, a little faster each hour, and it will never return. That is the strange and quiet truth astronomers uncovered at the very end of the 20th century. And it is the truth that gives our whole story its title. For most of the century, the great open question about cosmic expansion was not whether it was happening, but how it would end. Hubble had shown that space was stretching and the galaxies were drifting apart. The natural assumption was that gravity, the patient pull of all the matter in the universe tugging on all the rest, would gradually slow that expansion down. The only real question seemed to be whether gravity would slow it just enough to coast forever, or whether it would eventually halt the expansion altogether and pull everything back together. Either way, the expansion was expected to be losing steam. The cosmos was thought to be applying its brakes. To find out how hard those brakes were being pressed, two rival teams of astronomers set out in the 1990s to measure the expansion across enormous distances. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, its name drawn from the astronomers' shorthand for redshift, headed by Brian Schmidt at the Mount Stromlo Observatory in Australia, and Nicholas Suntsev at the Cerro Tololo Inter-American Observatory in Chile, with the support of Robert Kirshner, the same astronomer whose team had charted the great Botha's Void years before, and who had trained many of the group's members. Among them was a young researcher named Adam Rees, the same Rees whose later work we met in the Hubble tension. Both teams used the same elegant tool, a particular kind of stellar explosion called a type Ia supernova. These supernovae are remarkable because they explode with very nearly the same true brightness every time, like identical bulbs of a known wattage scattered across the cosmos, and that consistency makes them precious. If you know how bright a bulb truly is, and you measure how dim it looks from where you stand, you can work out exactly how far away it must be. By finding these exploding stars in very distant galaxies and measuring how faint they appeared, both teams could measure cosmic distances with new precision and compare those distances to the redshifts to see how the expansion had behaved over billions of years. In 1998 and 1999, both teams arrived at the same astonishing result, the High Z team in a paper led by Adam Rees and built on a study of just 16 of these exploding stars, with Perlmutter's team confirming the picture close behind. And it was the opposite of what anyone expected. The distant supernovae were not just far away, they were fainter, and therefore farther than they should have been if the expansion was slowing down. The universe was not applying its brakes at all. It was pressing the accelerator. The expansion was speeding up. The galaxies were drifting apart faster and faster with every passing era, and they had been doing so for billions of years. It was such a surprising finding that the teams checked it carefully before believing it, and the discovery would later earn Perlmutter, Schmidt, and Rees the Nobel Prize in Physics. But it left a profound puzzle in its wake. If gravity pulls everything together, and the expansion is nonetheless speeding up, then something must be pushing outward, something strong enough to overpower the combined gravity of every galaxy in the cosmos. Astronomers did not know what it was. They still do not really. And so they gave it a name that is really just a confession of mystery. They called it dark energy. Dark energy is the name we give to whatever is driving the acceleration. And the strangest thing about it is how much of the universe it appears to be. When astronomers add up the full energy budget of the cosmos, the ordinary matter that makes up stars and planets and people accounts for only about 5%. Another quarter or so is dark matter, a separate invisible substance whose gravity helps hold galaxies together, and all the rest roughly 68% of everything, the largest share of the entire universe, is this dark energy. It is not concentrated in stars or galaxies. It appears to be a property of empty space itself, a faint outward pressure woven into the vacuum, so that the more space there is, the more dark energy there is to push it wider still. And that last detail is the key to our title. Because dark energy lives in space itself, the expansion feeds on its own success. As space stretches, there is more space, and more space means more dark energy, and more dark energy means faster stretching, which makes still more space. It compounds gently and relentlessly. In our best and most thoroughly tested model of the cosmos, a model astronomers call lambda CDM, dark energy behaves as a true constant, an unchanging pressure that never tires and never fades. Physicists capture this behavior in a single number, called the equation of state, which for a perfectly constant dark energy sits at a value they write as -1. As long as that number stays fixed at -1, the outward pressure never changes its character, and the conclusion is as simple as it is profound. The expansion does not slow. It does not stop. It accelerates forever, and the distance between the unbound galaxies grows without end. The tide goes out, and it never comes back in. That is what we mean when we say it won't stop. Under our best current understanding, it truly won't. And yet, in keeping with the honesty that runs through this whole story, we should hold even that conclusion with open hands, gently, the way you would hold something you care about but do not fully own, because the most recent measurements have begun, very softly, to raise a question. In March of 2025, the team behind the Dark Energy Spectroscopic Instrument, a project mapping the positions of millions of galaxies to chart the expansion with extraordinary precision, released a major set of results known as DESI-DR2. When astronomers combined these new measurements with the early universe data from the cosmic microwave background and with the supernova observations, they noticed something intriguing. The combined data hinted, very mildly, that dark energy might not be perfectly constant after all. In the language of that equation of state, the data left a little room for the number to drift slightly away from -1, rather than sitting locked there forever. It hinted that the outward pressure may have been very slightly stronger in the past, and could be slowly, gently weakening over cosmic time. It is important to be careful and calm about exactly what this means, because it is easy to overstate in either direction. The hint is real, and it is the kind of thing that makes cosmologists lean forward in their chairs. But it hasn't yet reached the level of certainty that physicists require before they will call something a discovery. The standard picture, with its constant, never-fading dark energy, still fits the data well. The signal is a tantalizing whisper, not a settled fact. It may strengthen with future measurements into something revolutionary, or it may fade away as the data improve. What it tells us tonight is something rather beautiful. The ultimate fate of the universe, whether the drifting truly continues forever, or whether the cosmos has some subtler future in store, remains, even now, an open question. We have written it on the door of our story in our best ink, and we have left a little room beside it for the universe to surprise us. That is not a failure of the science. That is the science still breathing, still listening, still willing to be astonished. Picture, then, a quiet escalator in an empty museum late in the evening, carrying you slowly upward through the soft light toward a wide and open gallery above. It moves gently, almost imperceptibly, and yet, if you pay close attention, you can feel it carrying you a little faster as it goes. easing you outward and upward into the open space ahead, unhurried, steady, and without any sign of stopping. That is the expanding cosmos, accelerating so gently that you would never feel it, opening the distances wider with every quiet moment. So the distances grow, and the growth speeds up, and under our best model, it will not stop. But we have left two important promises only half kept. We have said the growth applies to the unbound galaxies, and that our own family holds together. It is time, at last, to look closely at exactly what the expansion can pull apart, and what it cannot touch at all. Here is the gentle distinction that makes our whole title honest, and it is worth slowing down for, because it is the warmest idea in the entire night. Cosmic expansion is a selective thing. It does not stretch everything. It stretches only the empty, unbound space between things that are too far apart to hold on to one another. Within any system where some force is actively holding things together, the expansion simply does not take hold. It is overruled quietly and completely by whatever binds that system, and almost everything you know and love falls into that protected category. Think about the scales where this matters. The atoms in your hand are held together by the electromagnetic force and the forces within their nuclei, bonds vastly stronger than the faint outward pressure of dark energy. So atoms do not expand. Your body, woven from those atoms, does not expand. The chemical bonds holding a stone or a tree or a sleeping cat together are not loosening. The earth beneath you is held in its shape by its own gravity and the strength of rock, and it is not growing wider. The earth's orbit around the sun is governed by the sun's gravity, a grip far too firm for the expansion to pry open, so our orbit is not slowly stretching outward. The entire solar system is bound, and bound things stay bound. The expansion does not add a single inch to the distance between the earth and the sun, nor to the room where you are resting tonight. This is the crucial point that careful listeners sometimes worry over, and the answer is reassuring. The growing distance in our title does not mean the universe is slowly tearing apart everything in it. It is not creeping into your bones or loosening the ground or pulling the planets from their paths. It only acts across the vast, empty, unbound gulfs, the spaces between galaxies and groups of galaxies that have no shared grip strong enough to resist. Those are the only distances that grow. Everywhere a force holds firm, the cosmos lets that small thing keep its shape. And gravity, it turns out, holds firm across surprisingly large scales. We saw this already with our local group, our family of galaxies moored together in the same harbour. The mutual gravity of all those galaxies is strong enough to have decoupled the whole neighbourhood from the expansion long ago. So the Milky Way and Andromeda and Triangulum and all their dwarf companions are not flying apart. They are bound. They will stay together while the wider universe drifts on without them. Gravity has won here, and it will go on winning here for as long as the family endures. Which brings us back, at last, to Andromeda, and to the promise we made when we first found it drawing closer rather than receding. We said we would return to resolve the mystery, and now we can. For a long time, the story astronomers told about the Milky Way and Andromeda was a story of certain collision. The two great galaxies were approaching. Gravity was drawing them together, and the textbooks confidently predicted a grand merger a few billion years from now, the two spirals winding into one another and eventually settling into a single combined galaxy. It was treated as near inevitable, a fixed appointment in the deep future. But here is one of those lovely moments where better measurement softens an old certainty. In 2025, an international team of astronomers led by Sawala published a careful new analysis in the journal Nature Astronomy. They combined precise observations from the Hubble Space Telescope with extraordinarily accurate measurements of the galaxy's motions from the European Space Agency's Gaia mission, a spacecraft built specifically to chart the positions and movements of stars with unprecedented precision. And when they ran the numbers, fully accounting for the gravitational influence of the other members of the local group, the certain collision dissolved into something far more open. What they found is that the merger is now closer to a coin flip. Over the next 10 billion years, the chance of the Milky Way and Andromeda actually colliding works out to somewhere around 50%. And within the next 5 billion years, the window the old textbooks pointed to, the odds drop to only about 2%. A clean collision is far from guaranteed. In many of their simulations, the two galaxies sweep past one another, or settle into a long, slow dance without ever truly merging. The reason for this surprising softening is itself rather beautiful, and it comes down to the quiet influence of the smaller members of the family. The chief of these is the Large Magellanic Cloud, the dwarf galaxy orbiting our own Milky Way that we met a little earlier. Its gravity tugs gently but persistently on our galaxy, pulling us slightly to one side, just enough to nudge the Milky Way off the head-on path it would otherwise follow toward Andromeda. The Triangulum galaxy, M33, plays into the balance too, pulling on Andromeda in its own turn. When Sawala and his colleagues ran the encounter forward many thousands of times, letting all of these gentle competing pulls play out, they found that in roughly half of those possible futures, the two giants slip past one another rather than colliding. That small sideways nudge from a little companion, accumulated over billions of years, is often enough to turn a direct hit into a near miss. A companion easy to overlook quietly helps decide the fate of the two largest galaxies in our neighborhood. There is something fitting in that. All through this night, we have watched our certainties soften under more careful measurement. The Hubble constant carries a genuine tension. The Andromeda collision becomes a coin flip. Even the forever acceleration of dark energy has begun to whisper a question. And none of these softenings are losses. Each one is the science breathing, the picture growing more honest and more interesting rather than less. The universe keeps gently reminding us that it is larger and subtler than our tidiest stories, and that there is real wonder in not yet knowing. But whatever the precise outcome, whether the two galaxies merge in a slow spiral, or sweep past one another in a long, graceful pass, the deeper truth holds. The Milky Way and Andromeda are bound. They are family. The expanding universe is not carrying them away from each other. They will share the same small patch of the cosmos for as far into the future as we can meaningfully see, while the unbound galaxies far beyond our family drift away without end. And this is the heart of the whole night, the thing worth carrying with you as you rest. The universe is letting go of the distant and the unbound, opening the great gulfs wider and wider, releasing the far galaxies into a darkness from which they will never return. But it is not letting go of the small family each galaxy belongs to. It lets the distant islands drift. It keeps the close ones. The cosmos, for all its vast and patient stretching, leaves us our neighbors. It leaves us the harbor. It lets us keep the people and the planets and the small, bright family of galaxies that we belong to. Picture a small family gathered in a circle on a dark beach at night, holding hands, their feet planted in the cool sand. A shallow stream of seawater flows in around their ankles, soft and steady, finding its way between and around them, flowing on past toward the wider dark. The water moves all around them, but it does not break their grip. It cannot carry them apart. They simply stand there together, hands joined, while the gentle tide flows harmlessly by and out into the night. That is what the expansion does to a bound family. It flows around us. It does not take us. It opens the wide dark beyond while leaving the circle of joined hands exactly as it is. We have kept our promise now. We understand what the expansion can pull apart and what it leaves untouched. And we understand that our own small family is safely among the things it leaves alone. But out beyond the harbor, in the realm of the unbound, the expansion does something so strange that it sounds at first like it should be impossible. Out there, galaxies are racing away from us faster than the speed of light itself. And somehow, no law of physics is being broken at all. That is the quiet paradox we will gently untangle next. Out beyond our harbor, in the open sea of the unbound, the expansion does something that sounds at first like a contradiction. There are galaxies in the distant sky that are receding from us faster than light can travel, and yet no rule of physics is being broken, and those galaxies are not, in any ordinary sense, moving at all. To see how both things can be true, we need to set down one of our oldest assumptions very gently and pick up a stranger and more accurate one in its place. The assumption to set down is this: most of us carry a deep instinct that nothing can travel faster than light, and that instinct is correct as far as it goes. Einstein's special theory of relativity does set a firm speed limit on the cosmos, but it is worth being precise about exactly what that limit forbids. Relativity says that no object can move through space faster than light. It is a rule about things traveling from one place to another, a runner sprinting across a field, a spacecraft crossing the void, a beam of light racing between the stars. Nothing moving through space may outrun light. What relativity says nothing about, because nothing in our everyday experience prepares us for it, is the stretching of space itself. The speed limit governs motion through space. It places no limit at all on how far space can grow. And that distinction, subtle as it sounds, is the whole resolution to the paradox. Let us build the picture slowly, with an image. Imagine you are standing at one end of one of those long moving walkways you find in airports, the kind that glides you gently forward. Now imagine the walkway is not a single belt, but is somehow stretching along its whole length, every section of it growing longer at once. A friend stands far down the walkway from you. Neither of you is walking. You are both standing perfectly still on the surface, and yet the distance between you grows, because all the walkway between you is lengthening at the same time. The farther apart you stand, the more stretching walkway lies between you, and the faster the gap opens up. If your friend stood far enough away, with enough stretching surface between you, the distance could open faster than you could ever close it at a walk, even though neither of you has taken a single step. That is precisely what happens to the distant galaxies. Each one rests quietly in its own local patch of space, going nowhere, much as we rest in ours. But between us and a very distant galaxy lies an immense volume of space, and every cubic stretch of it is expanding. Add up all that stretching across billions of light years, and the total can amount to a recession faster than light. Not because the galaxy is racing through space, which it is not, but because there is simply so much expanding space lying between us. The galaxy is still, the space is growing, and growing space obeys no speed limit. This gives us a natural boundary, a particular distance with a special meaning. Out at a certain range, The total expansion of all the space between us and a galaxy adds up to exactly the speed of light. That distance is called the Hubble radius, and it currently sits at around 14 billion light-years. A galaxy right at that distance is receding from us at precisely light speed. A galaxy beyond it is receding faster than light. The Hubble radius is not a wall or an edge of anything. It is simply the line where the accumulated stretching of space reaches the speed of light, the threshold past which galaxies slip into superluminal recession, carried by space alone. Now, you might reasonably ask a question here, and it is a good one. If those distant galaxies are receding faster than light, then how can we see them at all? How does their light ever reach us, if the space between is growing faster than light can cross it? It feels as though their light should be swept away, unable to make any headway against the tide. The answer is one of the most quietly elegant ideas in cosmology, and it rewards a moment of patience. The light we see from a very distant galaxy tonight did not set out under tonight's conditions. It left that galaxy long ago, sometimes billions of years ago, when the galaxy was far closer to us than it is now, and when the space between us was expanding less fiercely. Remember the rising bread and the inflating balloon from earlier, and now imagine running them backward. The further into the past you look, the smaller the whole universe was, and the closer together everything sat. The faintest galaxies in that deep field photograph we began the night with sent out their light when the universe was only a few % of its present age, when the gap between them and the patch of space that would one day become us was a small fraction of what it is today. So that ancient light began its journey across a much more modest distance, and only the long eons of expansion since have stretched the gap to its present enormity. That light has spent all the intervening time on a long, difficult swim toward us. In the early part of its journey, through regions where the expansion was gentler, it managed to make real progress, crossing into space that was not stretching quite so fast. Stretch by stretch, it worked its way into our slower expanding neighborhood, and at last it arrives at our telescopes. So we can indeed see galaxies that are, right now, receding from us faster than light. We are not seeing them as they are now. We are receiving light that escaped long ago, that swam against a gentler current, and that only just managed to reach our shore. There is something tender in that picture when you let it settle. The light from those galaxies is, in a sense, the last we will ever receive from many of them. It set out in an earlier and friendlier era of the cosmos, and it made the crossing while the crossing was still possible. The galaxies that sent it have since been carried beyond the reach of any new signal, but their old light still arrives, faithful and ancient, a message that left before the door quietly closed. Picture a swimmer treading water calmly in the middle of a wide, gentle river at twilight. The swimmer is not struggling, not racing anywhere, simply floating in place, at rest in their own patch of water. But the river itself is being slowly drawn apart at both ends, the whole current lengthening, so that a friend standing far downstream drifts steadily away. Neither the swimmer nor the friend is moving against the water. They are both at rest, and still the distance between them grows, gently and without effort, faster than the swimmer could ever close it, carried entirely by the quiet stretching of the river beneath them. That is a distant galaxy and our own, drifting apart on the lengthening river of space, each of us perfectly still, the gulf between us widening all the same. So galaxies recede faster than light, without anything ever moving faster than light, and their oldest light still finds us even as they slip beyond reach. That phrase, beyond reach, is the one we have not yet truly faced. We have spoken of galaxies receding and drifting and growing distant. But for the vast majority of the galaxies we can see tonight, the situation is more final than mere distance. They have already crossed a line, a threshold from which nothing we could ever send would catch them. And the number of galaxies on the far side of that line is far larger than you might expect. Begin with a single beam of starlight and think of it as a kind of fossil. When you look at a distant galaxy, you are never seeing it as it is. You are seeing the light it released long ago, a portrait preserved in transit, carrying news that may be millions or billions of years out of date. The galaxy in the image has aged since then, changed, perhaps drifted far from where the light shows it. In that sense, every photograph of the deep cosmos is a museum of fossils, ancient impressions of objects as they once were, arriving long after the moment they recorded. We have touched this idea gently before, with Andromeda's 2.5 million-year-old glow. Now we follow it to its quiet and remarkable conclusion. There is a particular boundary out in the dark, and it is the most final of all the lines we have drawn tonight. Astronomers call it the cosmic event horizon. To understand it, we have to keep 3 different distances clear in our minds, because they sound similar and mean very different things. The first is the observable universe, the full sphere of everything, whose light has had time to reach us since the beginning. Its edge lies about 46.5 billion light-years away in every direction, and within that vast sphere there are an estimated 2 trillion galaxies. The second is the Hubble radius, which we met a moment ago. The line at about 14 billion light-years, where recession reaches the speed of light. And the third, the one we turn to now, is the cosmic event horizon, which sits somewhere around 16 to 18 billion light-years away. The event horizon is the true line of no return, and here is precisely what it means. It is the boundary beyond which any signal we send out today, even a beam of light launched this very moment at the fastest speed the universe allows, can never reach. The space beyond that line is expanding away from us so quickly that nothing we emit will ever catch up to it. A galaxy past the event horizon is not merely far away. It is permanently, absolutely beyond our reach. We could never travel there. We could never send a message there. Nothing we do here will ever touch it, no matter how much time passes. And now the number that gives this section its name. Of the roughly 2 trillion galaxies in our observable universe, only about 6% remain even theoretically reachable. The other 94% have already crossed beyond the cosmic event horizon. They are still visible to us, glowing in our telescopes, their ancient light still arriving. But the galaxies themselves are already gone, already past the line, already in the realm from which no signal of ours could ever arrive. We can see them. We can never reach them. The window to make contact closed long ago, in most cases before our species existed, and we are only now receiving the last of the light that escaped while the window was still open. This figure comes from a straightforward piece of geometry, the kind of calculation the science writer Ethan Siegel has laid out clearly in his work, and it follows directly from our best model of the cosmos combined with the precise measurements of the Planck satellite. Picture 2 nested spheres centered on us. The outer one is the whole observable universe, reaching about 46.5 billion light-years in every direction. The inner one is the sphere we could still, in principle, reach, its edge set by the event horizon at roughly 16 billion light-years. Because the volume of a sphere grows as the cube of its radius, that inner sphere holds only a small fraction of the total volume, Take the ratio of 16 to 46.5, raise it to the third power, and you are left with only about 4 to 6%. So roughly 94% of everything we can see turns out to lie beyond any possible contact. It is not a guess or an estimate pulled from the air. It is a consequence of the expansion rate we have measured, applied carefully to the geometry of space. There is one more figure worth holding, because it makes the slow motion of all this tangible. The boundary is not static. As space continues to expand, more and more galaxies cross the event horizon, slipping from the reachable into the unreachable, quietly and continuously. When astronomers work out the rate, accounting for the matter contained in the regions crossing that line each year, it comes to something on the order of 160 billion stars passing beyond our event horizon annually. To put that another way, it is roughly the equivalent of a fully formed galaxy the size of our own Milky Way, or of Andromeda, slipping quietly beyond our reach every single year, steadily, without pause. It would be easy to let a number like that land as a sadness, and the older, more anxious way of telling this story often does just that. But the calm and accurate way to hold it is gentler and truer to what is actually happening. We are not watching galaxies vanish in any sudden or violent sense. They do not blink out. They do not go dark all at once. Their light continues to arrive for a very long time, fading and reddening with exquisite slowness across the ages. What we are really witnessing is something closer to the steady arrival of very old letters, posted long ago by senders who have since moved somewhere we can no longer write back to. The letters keep coming. They are beautiful, and they are real, and they carry faithful news of how things once were. We simply cannot send a reply. The correspondence has quietly become one-directional, an archive of ancient voices still speaking to us across a gap that can no longer be crossed in return. There is a strange comfort in framing it that way. The light is not being taken from us. It is, if anything, a gift that keeps arriving long after its source has passed beyond reach, a record preserved and delivered across spans of time we can barely imagine. We are the fortunate recipients of an enormous library of fossil light, written by senders we will never meet, and the reading of it is one of the quiet privileges of being alive in this particular era of the universe. Picture, then, a grand and silent library at midnight, its high shelves stretching up into soft shadow, lit only by a single warm lamp. On the oldest shelves stand books written in a faded golden ink that glows faintly with a light all its own. Each book holds the voice of an author who set down their words long ago and has since travelled somewhere far beyond these walls, somewhere you could never follow, somewhere from which no new pages will ever come. But the books remain. Their golden words still glow on the page. You can open any one of them and read, in the quiet, the faithful voice of someone who is no longer reachable, preserved exactly as they were, speaking gently across an unbridgeable distance. That is the night sky filled with the light of the 94%. A library of glowing ancient voices, still here, still speaking, still ours to read, even though their authors have long since passed beyond the door. So most of the galaxies we can see are already beyond our reach, archived in old light, drifting further into the unreachable with each passing year. But we have not yet asked where this widening happens fastest. The great voids we visited earlier, those enormous empty bubbles that make up most of the volume of the cosmos, turn out to play a special role in all of this. They are not merely empty. They are, in a quiet sense, the very engines of our growing isolation, and understanding why brings the whole picture of the expanding universe gently together. cast your mind back to the cosmic web, that vast and delicate scaffolding we explored a while ago. The bright filaments of galaxies strung like beads on threads, the dense glowing nodes where those threads meet, and wrapped all around them, taking up most of the volume of everything, the great empty bubbles we called voids. We left that picture with a quiet observation that the bubbles were not still, that they were slowly growing. Now we can understand why they grow the way they do, and why they matter so much to the story of our deepening isolation. The key is something we learned when we talked about what the expansion can and cannot pull apart. Expansion takes hold most powerfully where there is the least matter to resist it. Wherever gravity has something to grip, a cluster of galaxies, a dense filament, a bound family like our own, that gravity pulls inward and holds the local space together, refusing the outward stretch. But in a place with almost no matter at all, there is nothing to do the gripping. There is no inward pull to balance the outward push of dark energy. And so the expansion proceeds there essentially unopposed, at its full and undiminished strength. That is exactly the situation inside a great cosmic void. A void is, by definition, a region nearly empty of matter, with far too little gravity to resist anything. So within the voids, dark energy stretches space at close to its maximum possible rate, faster than the average across the cosmos as a whole. The emptiest regions are precisely the regions that expand the fastest, because emptiness is what lets the expansion run free. The voids are not passive holes that the universe happens to contain. They are active, swelling, growing fastest of all, the most expansive places in all of creation. And as each void swells, it presses outward on everything around it. The filaments and walls of galaxies that form the boundaries of the bubbles are gently pushed apart by the growth of the empty regions between them. Picture the voids as expanding cushions, each one inflating, each one shouldering its neighbors aside, so that the bright threads of galaxies caught between them are eased steadily farther from one another. The galaxies themselves are not doing anything. They are riding on the boundaries of bubbles that are quietly inflating beneath them, carried apart as the empty spaces between them grow. There is a measurable difference between these regions, and it grounds the picture in real numbers rather than mere imagery. In the dense filamentary walls, where the warm, hot, intergalactic gas we found earlier is concentrated, the matter density can run anywhere from 10 to 100 times the cosmic average, with perhaps a few particles per cubic meter. That gas is also genuinely hot, shock heated to temperatures of 100,000 up to 10 million degrees as it settles and collides along the filaments, though, just as we found earlier, far too thin to warm anything you might send through it. That density is still extraordinarily sparse by any earthly standard, but it is enough gravity to anchor the region and slow its stretching. Inside the deep voids, by contrast, the density falls well below the cosmic mean, often to less than a tenth or a fifth of the average, and what little gas lingers there is cooler, an emptiness within the emptiness. With so little there to hold anything back, the void expands freely while the denser walls around it hold their ground. The contrast between the two is the engine. The full, anchored filaments resist, the hollow voids stretch unopposed, and the difference between them slowly reshapes the geography of the universe. And it is not only ordinary matter that is absent from the voids. When astronomers map the invisible dark matter, the unseen substance whose gravity helps shape the entire cosmic web, they find that the voids are empty of that too. A void in the distribution of galaxies is also a void in the distribution of dark matter. So inside these great bubbles, there is truly almost nothing. not the glowing gas, not the stars, not even the hidden dark matter, to provide any inward pull against the outward stretch. There is a further subtlety here, gentle but rather elegant. Over the long ages, whatever thin matter does linger inside a void slowly drains outward, drawn by the gravity of the denser walls that surround it, so that the void grows emptier still with time. An emptying void behaves, in effect, like a region of slightly less than average gravity, a place that not only fails to resist the expansion, but quietly helps to push its own boundaries outward. The emptiest places in the cosmos are not merely swept along by the widening. In their own soft way, they help to drive it. This is the deeper meaning of our title's promise. The growing distance between galaxies is not a single uniform stretch applied evenly everywhere. It is a textured, living process. Fastest in the emptiest places, slowest where matter gathers and holds. The isolation of the galaxies is not a fixed condition that was set once and left alone. It is something happening actively, continuously, with every passing era. The gap a galaxy faces across the void beside it is a little wider every million years, and the bright threads of the cosmic web drift a little further apart with each turn of cosmic time. The architecture of everything is in slow, patient motion, opening outward from its emptiest rooms. It is worth pausing to notice how gentle this process actually is, despite the enormous scales involved. Nothing is being torn. Nothing is straining or breaking. The voids do not push violently. They expand with a slowness so profound that within any single human lifetime, or within all of recorded human history laid end to end, the change is utterly imperceptible. The filaments ease apart over spans of millions and billions of years, far too slow for any eye to catch. What we are describing is not a rupture, but a drift, the most patient drift imaginable, the quiet opening out of space from the inside of its emptiest bubbles. Picture a wide and peaceful meadow on a still summer afternoon, dotted here and there with small groves of trees. Between the groves wind broad grassy clearings, open and sunlit and empty. Now imagine that those open clearings are very slowly widening, year by year, so gradually that no one walking through could ever notice it within a single season. The groves themselves are untouched. Every tree stays exactly where it stood, roots firm, branches whole. But the empty clearings between them spread, patiently and without sound, easing the groves a little farther apart with each passing decade, so that what was once a close-gathered woodland becomes, over ages, a scattering of separate groves across a widening field. That is the cosmic web in motion. The galaxies are the groves, intact and whole. The voids are the clearings, quietly spreading. And the slow widening of the empty places is what carries the bright islands of the universe gently apart. We have followed the growing distance now from nearly every angle. We have seen why space stretches, why the stretch accelerates, what it can and cannot pull apart, how galaxies recede faster than light, how most of them have slipped beyond our reach, and how the empty voids drive the widening fastest of all. There remains one direction left to look, and it is the longest view of all. If the distances keep growing gently and without end, then what becomes of the universe in the deep future, on the order of 100 billion years from now? What would the sky look like to someone gazing up from our merged and quiet family, long after the rest of the cosmos has drifted away? That is where our journey turns next, into the far and patient future. Let us travel forward now, far past any timescale we have yet considered, into the deep future of the cosmos. Not thousands of years ahead, nor millions, but on the order of 100 billion years, a stretch of time so long that the entire present age of the universe, all 13.8 billion years of it, would fit inside it many times over. We are going to stand in imagination on a world in that distant era and look up at the night sky to see what remains. To picture it honestly, we should first follow the threads we have already laid down to their natural conclusion. The expansion continues, gently and without end, opening the great gulfs wider with every passing age. The galaxies beyond our family, already receding, already mostly past the event horizon, drift steadily farther into the unreachable dark. One by one, over the long ages, their ancient light finishes arriving, stretches into invisibility, and fades from view. And our own family, the local group, continues to do what bound families do. It holds together. Over those vast spans of time, the Milky Way and Andromeda and their companions will very likely have drawn into a single merged galaxy, a great combined island of stars that astronomers sometimes playfully call Milkomeda, settled and quiet at the center of our small surviving neighborhood. So here is the sky that a future astronomer would see, somewhere around 100 to 150 billion years from now. Looking outward in every direction, they would find their own galaxy, the merged remnant of our family, full of stars and structure and light. And beyond it, in every direction, they would find nothing. No other galaxies. No distant smudges of light to catch the eye on an autumn night. No faint glow of a neighboring island across the dark water. Every galaxy that was not part of their own bound family will have receded so far and so fast that its light can no longer reach them at all. The sky beyond their own galaxy would be perfectly, uniformly black. There is a particular consequence of this that is worth sitting with, because it is one of the most thought-provoking ideas in all of cosmology, and it turns on something gentle rather than frightening. That future astronomer, gazing into an empty sky, would have no way to discover that the universe is expanding. Think about how we came to know it ourselves. Everything we have learned tonight rested on being able to see other galaxies. Hubble discovered the expansion by measuring the redshifts of distant galaxies, by watching their light stretch as they receded. The whole edifice, the expansion, the acceleration, dark energy, the cosmic web, the entire story, was built on the fact that there are other galaxies out there to observe. But in that far future, there would be none to see. A brilliant astronomer of that era, with perfect instruments and a sharp and curious mind, could look as hard as they liked and find no redshifted galaxies, no standard candles flickering in the distance, no evidence of any kind that space was growing. As far as they could tell, their single galaxy would appear to sit alone in a static and unchanging void, the way our own ancestors once imagined our galaxy to be the whole of creation. The expansion will not have stopped. It will simply have hidden every trace of itself. The very process of the universe spreading out will have carried away all the evidence that it was ever spreading at all. A future science, however advanced, might never guess at the grand expanding cosmos that we can read so plainly in our own sky tonight. The record will have quietly erased itself. This is the work of the astrophysicists Lawrence Krauss and Robert Scherer, who in 2007 published a paper with the wonderfully evocative title, The Return of a Static Universe and the End of Cosmology. They worked through exactly this future, showing that as the accelerating expansion carries everything beyond the horizon, the observable universe shrinks back down, in a sense, to a single island, and the deep truths we have uncovered become, for all practical purposes, undiscoverable. Consider what happens to the one clue that might otherwise survive. Filling all of space, in every direction, is the faint afterglow of the Big Bang itself, a whisper of microwave light called the cosmic microwave background, the oldest light in existence and the clearest evidence we have that the universe had a hot, dense beginning. It is one of the great anchors of everything we know about cosmic history. But Krauss and Scherer traced its fate too. By that same distant era, around 100 billion years from now, the relentless stretching of space will have drawn the waves of that ancient light out to enormous lengths, on the order of a meter from crest to crest, sliding it down out of the microwave range and into faint, long radio waves. And its intensity will have dropped by something like 12 orders of magnitude, a trillion-fold dimming, until it fades below anything a future instrument could plausibly detect. The afterglow of the beginning, still washing gently over us tonight, will by then have been stretched and quieted into silence. The clues will be gone, every one of them. It would be easy to read this as a kind of loss, a melancholy ending. But there is another way to hold it, and it is the way that fits the quiet wonder of this whole night. What that future picture reveals is not how poor those distant astronomers will be, but how fortunate we are. We happen to live in a particular fleeting window of cosmic time, an era when the universe still wears its history openly across the sky. The galaxies are still visible. The redshifts are still readable. The afterglow of the beginning still washes faintly over us, waiting to be measured. We arrived early enough to see the evidence, and late enough to understand it. That is an extraordinary piece of timing, a brief and golden chapter in the long life of the cosmos, and we are here to read it while the reading is still possible. That is not a reason for sorrow. It is a reason for a kind of quiet gratitude, the feeling of having arrived at the gallery while the great paintings are still on the walls, before they are gently taken down for the long, dark ahead. Picture, then, a warm cabin deep in the woods on a winter midnight, its single window glowing with the soft amber light of a fire within. Far across the valley, scattered up the distant hillsides, the lights of neighboring homes once flickered through the trees, small and far away and companionable. But over the long hours of this endless night, one by one, those distant lights have gone out, until at last the valley beyond the window holds only darkness. And yet, inside the cabin, nothing has changed. The fire still burns. The room is still warm. The small circle of light around the hearth is as steady and as bright as it ever was. The distant lights have gone, but the home remains, snug and whole, glowing quietly against the dark. That is the far future of our family, alone in an empty valley, perhaps, but warm and intact, and entirely at peace. So the sky will one day empty, slowly and gently, leaving our merged family glowing alone in a quiet dark. We have nearly completed the great arc of the journey now. But there is one more limit the expansion places on the cosmos, subtler than distance, that touches on the very possibility of speaking across the void. Even within the small fraction of the universe that remains reachable, the growing space does something quiet to any message that tries to cross it, an understanding that brings us to the closing of the great window. There is one last way the growing distance shapes the cosmos, and it is the quietest of all. It has to do with what happens to a message sent across the widening dark, and it turns out that the very space carrying a signal also gently silences it. We have already met the heart of the mechanism, back when we stood with Edwin Hubble on his mountain. When light travels across expanding space, the space stretches the light along with everything else. The waves of a beam of light sent out at one length arrive longer than they began, drawn out by all the expansion that happened during the journey. This is redshift, the stretching of light toward the red end of the spectrum and beyond. We saw it as the fingerprint that revealed the expansion. Now we can see it as something with consequences of its own, because a stretched wave of light is not merely a different color. It is a weaker one. The energy a beam of light carries is bound up in the length of its waves. Short, tightly packed waves carry more energy. Long, drawn-out waves carry less. So as light crosses the expanding cosmos, and its waves are stretched longer and longer, the light loses energy along the way, drained gently by the very growth of the space it is crossing. A signal that left a distant galaxy as bright visible light might arrive after a long enough journey, shifted all the way down into the infrared, then into microwaves, then into faint long radio waves, growing quieter and softer and more diffuse with every stretch of expanding space it passes through. The expansion does not block the signal. It simply tires it out, draining its strength across the megaparsecs until what arrives is a faint and reddened whisper of what set out. We do not have to imagine this draining in the abstract, because we are bathed in a perfect example of it, every moment of every day, filling all of space, arriving from every direction at once, is the afterglow of the Big Bang, the oldest light there is, which set out when the young universe was a searing, brilliant fireball. In the roughly 14 billion years since, the expansion of space has stretched the waves of that light by a factor of about 1,000, drawing them out from the bright, energetic wavelengths they began, with all the way down into faint microwaves. By that same factor, the light has cooled, until today it glows at a temperature of just under 3 degrees above absolute zero, colder than very nearly anything else astronomers measure. It is so stretched, so drained, so gentled by its long journey through expanding space, that our eyes cannot see it at all. We need delicate instruments to detect it. The faint, even hum that spacecraft, like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, were built to map. That whisper of cold light is the expansion's handiwork made plain, a signal once dazzling beyond imagining, quieted over the eons into the softest glow in the sky. This places a quiet natural limit on the very idea of communication across the cosmos. Imagine for a moment the hope of some grand conversation between galaxies, a message sent and an answer received. The expansion works softly against that hope in 2 ways at once. First, it drains the message, stretching and weakening it until, across great enough distances, it fades below anything that could be detected at all. And second, even where a signal could in principle still arrive, the sheer scale of the distances turns any exchange into something that is barely a conversation. A message crossing intergalactic space might take millions of years to arrive. A reply would take millions more to return. By the time any answer came back, the civilization that sent the first message, if such a thing existed, would have changed beyond recognition, or faded entirely, many times over. So a cosmic dialogue across the great gulfs is not really a dialogue at all. It is, at most, a monologue across the ages, a single voice speaking outward into the dark, with any reply arriving in an era so distant that the original speaker is long gone. The expansion ensures that the universe, on its larger scales, does not converse. It only sends slow, fading messages outward, each one a kind of letter dropped into a current that grows ever wider, carried away faster than any answer could ever return. It would be possible to find this lonely, and the older and more anxious way of telling the story sometimes does. But there is a calmer, and I think, a truer way to hold it, and it fits the gentle character of the cosmos we have been exploring all night. These limits are not hostility. The universe is not refusing to let its parts speak to one another out of any coldness or cruelty. The silence is simply a feature of enormousness, of patience, of scale. The cosmos is not a hostile place that mutes its inhabitants. It is a vast and unhurried one, so large and so slow that conversation across its full breadth was never really on the table to begin with. There is no malice in the quiet. There is only size and time, and the gentle stretching of space. And in that, there is something oddly familiar, something almost companionable. The universe is patient beyond all measure. It is in no rush to carry its messages anywhere quickly, no rush to demand a reply, no rush to do anything at all. It lets its light travel for billions of years without complaint. It lets its galaxies drift apart over spans that dwarf the entire history of life on Earth. It moves at a pace so slow that within any human life or any human civilization, the great changes are wholly invisible. There is a kind of deep calm built into the very fabric of the cosmos, a refusal to hurry that runs through everything from the drifting of galaxies to the long, patient journey of a single beam of starlight. The universe, in its enormity, is one of the most unhurried things there is, and there is comfort in keeping company with something so vast and so untroubled by time. Picture, then, a single voice calling out softly in a vast stone canyon at dusk. The sound travels outward, and the canyon walls return it, but each echo comes back a little softer than the last, a little deeper, a little more drawn out, the sharp edges of the words smoothing away into something gentle and low. The voice does not vanish all at once. It simply softens and lengthens and quiets, each return a touch fainter than the one before, until at last it blends seamlessly into the hush of the evening wind moving through the rocks. No longer quite a word, only a soft and peaceful sound, folding back into the silence. That is a signal crossing the expanding universe, sent out clear and bright, stretched and softened by the growing space, arriving at last as the faintest reddened whisper, gentle as a held breath, releasing into the quiet of a vast and patient dark. We have followed the growing distance now to the very limits of what it touches, out to the stretching of light itself, and the long, slow silence of the cosmic scales. The great journey outward is complete. We have travelled from a single deep field photograph all the way to the empty sky of the far future, and to the quiet that the expansion lays over any message sent across it. Now it is time to come home, time to leave the vast scales behind and return, gently, to the room where you are resting, and to ask the question that matters most as the night settles in. After everything we have seen, what does any of it actually change about the world, right here, right now, tonight? So we come home, back from the empty sky of the far future, back from the stretched and reddened whispers crossing the void, back through all those billions of light years to the small and ordinary room where you are resting tonight. And the question waiting for us here is the gentlest and most important one of the whole journey. After everything we have seen, the accelerating expansion, the 94% already beyond reach, the swelling voids and the emptying future sky, what does any of it actually change about your life, here, tonight? The answer is wonderfully simple. Almost nothing at all. The growing distance between galaxies, for all its grandeur, touches none of the things that make up an ordinary evening on Earth. The ground beneath you is exactly as solid as it was before you knew any of this. The air in your room has not thinned, the walls have not crept apart. We learned earlier that the expansion only takes hold across the vast, empty, unbound gulfs, and that wherever a force holds firm, the cosmos lets that small thing keep its shape, and everything near you tonight is held firm. The atoms of your body are bound tightly together, untouched by any cosmic stretch. The chair, the bed, the floor, the house, all of it is held by forces incomparably stronger than the faint outward pressure of dark energy. The Earth turns on its axis exactly as it always has. The moon holds its orbit. Tomorrow the sun will rise on its familiar schedule, having drifted not 1 inch farther from us across all the eons of cosmic expansion. Even the larger anchors of our existence are steady. Our sun has already been shining, calm and reliable, for about 4.5 billion years, and it has at least another 5 or 6 billion years of steady light still ahead of it before it begins the long, slow changes of its old age. It is a middle-aged star, in no hurry and in no danger, and it will hold the Earth in its familiar orbit far longer than our kind has yet walked the world. The stars you can actually see with your own eyes on a clear night, the few thousand scattered across the sky, are all members of our own Milky Way, all bound to us, all near neighbors within the same great spiral. Not one of the distant, receding, drifting islands we have spoken of tonight is visible to your unaided eye at all, save for that single faint smudge of Andromeda. And Andromeda, remember, is drawing closer. The night sky you actually step out under is, from edge to edge, a local and bound and familiar family, and the cosmic expansion touches none of it. The constellations your ancestors named will be recognizable for a very long time to come. The expansion changes the map of the very large and the very far, the relationships between galaxies separated by millions of light years. It does not change the sky you can see, nor the world you walk upon, nor the quiet rhythm of a single ordinary night. It is worth gathering up the honest threads of this whole story now, gently, the way you might fold a blanket at the end of the day, because the honesty is part of what makes it restful rather than unsettling. The first thread is that the growing is real. The distances between the unbound galaxies are genuinely increasing. The expansion is genuinely accelerating. And under our best and most thoroughly tested model of the universe, that growth continues without end. This is not speculation or scare story. It is the careful conclusion of a century of measurement, from Hubble's plates on Mount Wilson to the supernova surveys of the 1990s, to the satellites mapping the afterglow of the Big Bang. The drift is real, and it is gentle, and it is one of the deepest truths we have learned about the cosmos. The second thread is that the growing spares us. It applies only to the unbound, only to the great gulfs between distant galaxies and groups. Our own family, the local group, has long since decoupled from it and holds securely together. Andromeda, against all the old expectations, is drawing closer rather than away. The expansion is not pulling our neighborhood apart, and it never will. The cosmos lets go of the distant and the unbound, and it keeps the close. It leaves us, our family of galaxies, intact in the same small patch of the universe, for as far ahead as we can meaningfully see. And the third thread is the one we have held most carefully of all, the one we keep in open hands. That word, unstoppable, rests on dark energy remaining truly constant forever, and the very newest measurements, the DESI results released in 2025, have begun to wonder, very softly, whether even that is exactly so. The hint is gentle. It is not yet a discovery. The standard picture still fits the data well. But the question is real, and it is the kind of honest living uncertainty that ought to be stated plainly rather than smoothed over. The ultimate fate of the universe is, even now, an open question, and there is genuine wonder in that, the wonder of a science still listening, still willing to be surprised. These are not rhetorical flourishes dressed up to sound profound. They are the actual state of our understanding, told as honestly as we can tell it. The growth is real, it spares the family, and even the forever of it is something the universe may yet have more to say about. You can rest on all three of those at once, because all three are true, and none of them disturbs the ground beneath you or the breath moving quietly in and out of your body right now. There is, I think, a quiet dignity in a universe like this one. It is vast almost beyond comprehension, and it is patient beyond all measure, and it is gentle in a way that the older, more frightened tellings of this story always seem to miss. It opens its great distances slowly, without violence, without hurry, leaving every small-bound thing exactly as it is. It lets the far islands drift while it holds the near ones close. It is not a cosmos that threatens you. It is a cosmos that simply, calmly, goes about its enormous and unhurried work, while you rest safely within one small, warm, securely held corner of it. Picture a sturdy nest, woven tight and warm, cradled high in the branches of a great and ancient oak tree. All around it, through the vast canopy of the forest, a deep night wind moves through the leaves, stirring the farthest branches, swaying the distant treetops, carrying through the whole wide woodland in a slow and endless motion. But the nest itself does not stir. Tucked close to the trunk, sheltered and whole, it holds perfectly still while the great wind passes through the wider forest beyond. The branches far away may sway and shift in the dark, but here, in this one small woven place, everything is steady, everything is warm, everything is exactly as it should be. That is where you are tonight, held firm in one small secure corner, while the vast, quiet motion of the cosmos passes gently through the far reaches of the dark. We have very nearly reached the end of our journey now. There is just one last thing to do, one final return to make. We began with a photograph that looked crowded with light and turned out to be mostly darkness, and it is to that image and to the soft meaning hidden inside it that we will return as we let the night fully settle and the distance, at last, softens into rest. So let us return, at the very last, to where we began, to that single photograph of the deep sky, the one that opened our journey, crowded with its thousands of scattered galaxies like jewels spilled across black velvet. Picture it again now, softly, with everything you have learned since you first saw it. When we began the night, the image seemed to be a portrait of light, a gathering of bright islands pressed close together. But you understand it differently now. You know that the galaxies, real as they are not the true subject of the picture. The true subject is the dark. All that quiet blackness filling the space around the points of light. That is most of what the photograph actually shows, and most of what the universe actually is. The galaxies are the foam. The darkness is the sea, and the photograph that looks so full was, all along, a portrait of gentle, patient emptiness, with a scattering of warm light clinging to its surfaces. And that darkness, you know now, is not still. It is opening, slowly and without end, easing the distant islands of the cosmos apart with a patience that dwarfs all of human time. But here is the soft truth to rest on, the one we have carried through the whole night. This is not a tearing. It is not a violence done to the universe. It is a quiet opening out of space, a gentle widening of the dark between the far galaxies, so unhurried that within 100 human lifetimes it would not show at all. The cosmos is not breaking apart. It is simply, calmly, letting its islands drift, the way a still lake at dawn lets a scattering of leaves ease slowly away from one another across its widening surface. And while it does, it keeps the things that are close. We learned this, and it is worth holding as you settle toward sleep. The great expansion lets go of the distant and the unbound, but it spares the small family each galaxy belongs to. Our own neighborhood, the local group, holds securely together, moored by gravity, untouched by the cosmic tide. Andromeda drifts not away from us, but toward us. The sun holds the earth. The ground holds you. The whole vast drifting universe leaves our small warm corner of it, exactly as it is, held firm and steady in the dark. There is even, at the very edge of all this, a last soft uncertainty, and it is a kind one. The brightest minds we have are still not entirely certain that the drifting is truly forever. The newest measurements have begun to wonder, very gently, whether the expansion might one day have more to say for itself. We do not know, and that not knowing is not a worry to carry into sleep. It is simply the universe, vast and patient and full of quiet, keeping one last secret for some future night, some future mind, to slowly unfold. So this is what the distance between galaxies really is. Not a threat, not a horror, not a great cold loneliness creeping toward us. Only a soft and endless opening of space, a gentle drift of warm islands across a widening dark, with the small families held safely together while it happens. The photographs that looked so crowded were always mostly darkness, and that darkness was only ever a quiet, expanding space, letting the universe breathe slowly outward, in no hurry at all. You do not need to carry any of it with you into sleep. Not the numbers, not the names, not the vast distances or the careful measurements. Let them drift off the way the far galaxies do, softly and without effort. The ruler we built out of light, the nearest shore of Andromeda, the quiet family moored together in its harbor, the great empty bubbles opening slowly in the dark, the long and patient future of an emptying sky. You can set all of it down now. It will keep exactly as it is, whether or not anyone is holding it. That is one of the kindest things about this vast and unhurried cosmos. It asks nothing of you at all. It simply goes on, gently, while you rest. There is nowhere you need to be tonight. There is nothing you need to solve, nothing you need to hold on to. The universe has been drifting gently apart for nearly 14 billion years, and it will go on drifting long after this night has passed, slowly, patiently, without any hurry at all. You can let all of it go now. You can let your thoughts loosen and drift the way the galaxies do, softly, without effort, carried along by something larger and kinder than worry. Let your breathing slow. Let it lengthen, the way light lengthens on its long journey across the dark, growing softer and quieter, and more at ease with every passing moment. There is no distance you need to cross tonight. There is no message you need to send. There is only this small, warm, securely held place where you are resting, and the slow, gentle motion of a vast and unhurried cosmos far beyond it, asking nothing of you at all. Picture, as you drift, a quiet sheltered harbor at twilight. The water is dark and calm, and a handful of small boats sit moored together near the shore, side by side, their lines tied to the same worn posts, rocking ever so gently in the soft evening swell. Their lamps glow warmly, small steady points of light reflected on the still black water. And far out beyond the harbor wall, the wide dark tide stretches slowly toward the horizon, opening outward into the gathering night, vast and patient and endless. But the boats do not drift. Tied together, sheltered and close, they stay exactly where they are, glowing softly, rising and falling in the same slow rhythm, safe inside the quiet harbour while the great tide opens gently toward the dark. The distance is still growing out there beyond the wall,